Alright, so now I'd like to transition into a discussion of the energies of stereoisomers. So, how do we know whether two stereoisomers will react the same as each other or not? We would, of course, for instance, expect normal isomers, just your simple standard isomers, to react much differently because the connectivity of the atoms is different, and as we've seen, connectivity affects molecular orbitals, which is directly related to reactivity, as we'll explore more in Chapter 4. But for stereoisomers, it seems like they're a lot more similar, so they have the exact same connectivity, and so you might think they possess the exact same sets of molecular orbitals and maybe exhibit the exact same reactivity. However, that's not the case. So diastereomers, remember we identified diastereomers as a pair of molecules that possess the same connectivity but different internal distances within them. For instance, what I'm showing on this slide are, at the top here in red, the cis isomer of 2-butene. You can see the double bond in there and the two methyl groups sticking up. And then below in blue, I've got here the trans isomer of 2-butene. Drawn the trans isomer lowering energy because remember, in the trans isomer we alleviate the non-bonded interactions that are present in the cis isomer. Now the two methyl groups are far apart, so we don't see those same non-bonded destabilizing interactions. So what you can see is that difference in interatomic distances has a direct effect on stability, on the stability of these molecules. And although they're diastereomers and stereoisomers, they react significantly differently. So you'll notice what I'm drawing here for you is as the product simply butane. This reaction is the hydrogenation of these two isomers to butane. And what you see is that the reaction is a much more thermodynamically favorable process for the more stable trans isomer, and a much more thermodynamically unfavorable process for the cis isomer. However, we might expect, although I haven't drawn it here, that the activation barrier for the much more stable trans isomer will actually be higher. So the transition state here in blue may actually, in fact, be up closer towards the red, and getting over that activation barrier is actually more difficult for the trans isomer versus the cis isomer. Contrast that now with enantiomers, which are molecules that possess equal energies. They have the exact same internal distance matrices. They're just, the only way they differ is in shape. So for instance, of course, the classic example is your two hands, right? All of the internal distances within your hands are the same, and assuming the strength of your two hands is identical, with any non-handed object, your two hands will interact exactly the same way. Enantiomers exhibit the exact same properties. So what you're looking at here are two reaction coordinate diagrams, two diagrams of the progress of a reaction, two diagrams of the energy of the species within a reaction as a function of the reaction progress here on the x-axis. And what you can see is that I've drawn two enantiomers here of this bromophenyl compound. And these are two SN2 reactions, and they have the exact same energy. And that correspondence between the two is deliberate. So even though the molecules are enantiomers and the products are enantiomeric, notice that the products are enantiomeric as well, a consequence of that is that the energies of every species along the reaction coordinates, so everything from the reactant to the transition state down to the product, will all have the same energy. So in those reactions, the enantiomers will react equally well. So for instance, if we wanted to separate a mixture of the enantiomers, we couldn't use a simple SN2 reaction with a species like hydroxide to separate those enantiomers. We would simply get a racemic mixture of enantiomeric products. So that brings us to the question of how would you go about separating enantiomers? Well, how do we separate molecules that, for all intents and purposes, at least to us, appear to react identically? What we have to do is introduce another element of asymmetry into the system. And when we do that, we go from a mixture of enantiomers to a mixture of diastereomers. So the idea in terms of chemistry is illustrated here, and actually if you want to know more about this process in an abstract sense, I refer you to the wiki, hence the wiki alert, that talks about this process in terms of thinking about the hands and how you would separate a mixture of the hands through the use of a handshake. But here you see the idea illustrated chemically. So I've got two amino alcohols that are enantiomeric to one another, And I'm treating these with a compound that has a stereocenter. You can see it right there as a stereocenter. And when you do this, you form a new bond and introduce a new stereocenter into the product. So the R and S configurations of the starting enantiomers are maintained in the product, but there's only one configuration on the other side of these molecules, right? Because we only introduced one enantiomer of that bromophenyl compound. So the result is we get two diastereomers out. And remember what we saw 2 slides ago. Diastereomers differ in energy and differ in stability. So we can use this to separate the enantiomers. We could do anything, or the diastereomers, excuse me. We could do anything from react one diastereomer away to perform chromatography on the diastereomers. Many conventional separation techniques will work for the separation of diastereomers. There is one thing that kind of complicates the separation of enantiomers sometimes, and isolation of enantiomers. So even if you figure out a way to isolate an enantiomer in pure form, sometimes enantiomers can convert between each other through the process of what's called racemization. And the simple definition of racemization is the conversion of a pure enantiomer of a substance into a racemic mixture of that same substance. So it's the conversion of one enantiomer into another, in a sense. It can occur by a variety of mechanisms, but almost all of the time, I won't say all of the time because I've actually done a seminar on chiral mechanisms of racemization of enantiomers, but they all involve an achiral intermediate for our purposes. So what you're seeing at the bottom here is an example in which I've got this amino ketone interconverting between its two enantiomers. And what can happen is deprotonation of the hydrogen here leads to a planar achiral intermediate. So what you're looking at in the middle is actually a planar molecule. It possesses a plane of symmetry that's in the plane of the board, hence the blue box. And reprotonation of this achiral intermediate from the other side of the intermediate will generate the enantiomer of the starting compound. So take a minute, convince yourself that those two guys are enantiomers, and what you'll see is that this is essentially a racemization pathway that proceeds by deprotonation of that key hydrogen, followed by reprotonation of the resulting enolate on the other side. So we take off that hydrogen, that generates an achiral intermediate, and then we put it back on the other side of what was formerly a stereocenter, right? That's destroyed in the achiral intermediate that becomes a stereocenter again when we reapply that hydrogen to it.